The expected work per cycle of this engine is the area enclosed in the PV diagram. Therefore, it is the product of the change in pressure times the change in volume. The mass of the air in the canister is the volume of the system at the dead state, times the density of air. Since the temperature of the cold bath is known to be 0 degrees Celsius, and the temperature of the hot bath is 100 degrees Celsius, the initial volume can be calculated with the ideal gas law. The initial pressure is known to be atmospheric, and the increase in pressure is the pressure exerted by the applied mass. Therefore, the final volume may be calculated by the ideal gas law and looks like the following. V1 is equal to the mass times the air times R times the temperature of the cold water divided by the pressure at atmospheric. The P1 is equal to atmospheric pressure, and P2 is equal to the atmospheric pressure plus the pressure from the mass applied, which is mg divided by A, which is the cross-sectional area of the piston. And finally, the volume at point 3 is equal to the mass of the air times R times the temperature of the hot water divided by P2, which we just calculated. Because the changes in volume and pressures depend on the applied mass, the following graphs may be generated for different values of mass. Although the larger mass cannot be raised as high, the nature of the heat engine indicates that the increasing applied mass yields more usable work. In the end, we are forced to go with a system that operates only through one engine cycle. The rising piston turns gears that rotate a spool of thread to raise a mass. We raised a 400-gram mass 1 centimeter in height for a total of 0.004 joules of work. This deviates a lot from our predicted 0.7 joules of work, but it makes sense because the geometry of the piston cylinder prevented the air from expanding to its full predicted volume. In other words, the volume of the cylinder was less than the increase in volume from the expansion of air by the change in temperature. And this, of course, led to the much lower efficiency in our heat engine.
Our heat engine takes the advantage of the change in volume of air in a sealed canister piston system to do work by increasing the gravitational potential energy of a mass. We started with our cylinder in the ice bath. This correlates to point 1 on our PV diagram. The first phase of our PV diagram from point 1 to 2 was isochoric expansion. This phase occurs when the cylinder is removed from the ice bath and placed into the hot bath. Once placed into the hot bath, the temperature of the cylinder will rise until the pressure is large enough to overcome the weight of the piston and the pressure from the atmosphere. At that point, the piston will rise. Something to note is this process is isochoric, meaning the volume is constant and the volume will not change until there is enough pressure or it reaches a certain threshold that will allow the piston to move. In our calculations, we accounted for this pressure change by adding the atmospheric pressure and the weight divided by the area of the piston to find the new pressure at state 2. To establish a relationship for finding P2, we used Newton's second law to find an expression for the sum of forces in the y direction and then made the assumption that the piston accelerated very slowly. This assumption allowed us to set the sum of forces equal to 0. The change from state 2 to state 3 is isobaric expansion. Once the pressure under the piston is equal to the calculated maximum, P2, the piston will remain at that pressure and rise to the top of the piston tube. At that point, it has reached its maximum volume, which is found with respect to the temperature of the hot reservoir using the ideal gas law to solve for V2. The change from state 3 to state 4 is isochoric compression. Once the piston reaches V2, we move the cylinder back into the cold bath, which causes significant enough temperature change to move the piston. The idea was that at this point, the weight is lifted off as the temperature increases. Also, as the temperature decreases, the pressure drops until it reaches its initial temperature. Before the piston moves down, our goal was for a ratchet to stop the wheel from rotating backwards with the piston. This way, we could hypothetically store potential energy from each cycle and add them. The final state change in the cycle is from state 4 back to state 1, and this change is isobaric compression. At state 4, air has reached P1. At this point, the volume will decrease to its initial state as the pressure stays constant. Each cycle our engine goes through, the piston will lose more weight, thus the minimum volume it reaches will decrease. To start a new cycle, we place the engine back into the hot bath.
We initially made a ratchet and pawl mechanism. The piston had a rack attached to it vertically. As the piston moves up, the rack moves up and turns a stationary pinion. The pinion gear is attached to a ratchet gear. Two pawls are lined up with the ratchet so that it can only turn in one direction. A weight on a string is attached to the ratchet so that as the piston moves up and down, the string is wound up in only one direction and the weight moves up. As the piston moves up, thus turning the pinion counterclockwise, the ratchet turns in one direction. As the piston moves down, the pinion starts to turn clockwise, but the ratchet is caught by the pawls and locks until the piston starts moving up again. We plan to measure our stored potential energy as the weight of the mass times the height, delta z, was displaced. However, we built our system forgetting that in order for the ratchet gear to turn, it needed to be interfaced with the pinion gear. So as the pinion gear reversed directions, the ratchet stopped spinning. Since the two gears are connected, the pinion gear stopped spinning too, and our piston did not move down. We had the right idea, but our system was flawed. In order to fix this problem, we decided to attach a shaft to our pinion gear. The other side of the shaft was connected to the push pawl. As the push pawl turned counterclockwise, it would push the racket in one direction. The stop pawl would be oriented so that it allows movement counterclockwise. Once the piston starts to move down, the push pawl would turn in the other direction and the stop pawl would prevent the ratchet from turning. This way, our ratchet gear only moves in one direction. Again, this only worked in theory. However, the push pawl needed to move with 2 degrees of freedom, translate over an angle. With the pawl connected to a shaft, it only rotated, which is just 1 degree of freedom. This action would not allow the ratchet to be pushed, and again, we did not have a way for the ratchet gear to turn in only one direction. So we dumped the ratchet and pawl mechanism at the last minute and found a new one. We tried to mimic movement 123, which is a reciprocating rack mechanism. The rack was attached to the piston and moved up and down. The rack itself engaged with 2 half pinion gears. The half gears were interfaced with smaller gears that turned the middle gear. The middle gear only turned in one direction because of the mechanism, so the weight attached to it would only rise. The pinion gear moved clockwise from the down to up position, which turned the middle gear counterclockwise. The left pinion moved clockwise from the up to down position, which turned the middle gear counterclockwise. So as the piston moved up and down, the middle gear only turned in one direction. Since this was a last-minute design, we didn't come up with a design to catch the weight at the end of its path. So technically, once the 5 minutes were up, the weight would have fallen and our total work stored would be 0. As a quick fix, we attached 2 weights of equal mass, one on the left gear and one on the right, that moved down as the middle weight moved up. This created an equal force balance on the middle weight that allowed it to stay in place when the piston stopped moving. We said that these 2 weights were a part of the internal mechanisms of the system. We should have stayed with and improved our pawl and racket mechanism. In order to create the push pawl, we would have needed to design a mechanism that angled our piston in such a way that it was able to move the push pawl to interact properly with the large rotating gear. That way, each cycle, the push pawl would have moved the gear 1 ratchet forward, and the stop pawl would prevent it from moving back in the 3 phase of our cycle.